What are we really made of? When you get right down to it, we hear about atoms all the time, but are they really the end of the line, indivisible? Or is there maybe more to the story?
Welcome to the Deep Dive. Today we're taking a close look deep inside matter itself, exploring the structure of the atom, our goal. To trace the journey scientists took, uncovering the atom's inner workings, its fundamental particles. It's a story of questioning, discovery, and, well, completely changing how we see reality. And for you, especially if you're preparing for exams, academic or competitive, this is absolutely foundational stuff in chemistry and physics.
Absolutely. Understanding the atom structure isn't just, abstract knowledge. It's the key. It governs why materials behave the way they do, how chemical reactions happen. It really is central to chemistry, to physics, across pretty much all syllabi you'll encounter.
Okay, let's start at the beginning then. For ages, the atom was thought to be at the smallest piece, indivisible, like Dalton proposed. But what were the first hints that maybe atoms could be broken down further? Well, the very first clues actually came from something quite familiar, static electricity. Think about activity 4.1 in many textbooks, or just everyday things, combing dry hair,
Yeah.
right? And then the comb picks up little bits of paper.
Yeah, happens all the time.
Or rubbing a glass rod with silk, and it attracts a balloon. These simple actions show that objects can become charged just by rubbing. And that strongly suggested, well, there must be charged things inside the atoms themselves. It hinted that atoms weren't just neutral, indivisible balls.
Ah, okay. So static electricity was the crack in the door. Who opened it further?
Well, a huge step came around 1900, J.J. Thompson. He's credited with identifying the electron, which we denote as
Yeah.
He found it was this tiny, negatively charged particle with almost negligible mass.
No electron, right.
But what's really interesting is that even before Thompson, back in 1886, E. Goldstein had observed something else. He found these positively charged rays in gas discharge experiments called canal rays, and these eventually led to discovering the proton, PET+.
So positive and negative particles were found. How did they compare?
Good question. The proton has a positive charge that's exactly equal in magnitude to the electron's negative charge, just opposite in sign. But mass-wise, they're very different. The proton's much heavier, about 2,000 times the mass of an electron. We usually just take its mass as one unit, one atomic mass unit.
Okay, so finding these two, the electron and the proton, that must have immediately thrown Dalton's idea of an indivisible atom out the window, right?
Exactly. It directly challenged it. And it raised a new question. If an atom has both a negative electron and a positive proton, their charges should balance out.
Making the atom electrically neutral overall.
Precisely. Which fits with our general observation of matter.
So they knew about these charged bits inside. The big puzzle then became, well, how are they arranged? How did Thompson first try to picture this?
Right, that was the million-dollar question.
Yeah.
Thompson proposed the first real model. It's often called the Christmas pudding or watermelon model. You might have heard of it.
Vaguely, yes. How did it work?
He pictured the atom as a sphere made of uniformly spread positive charge. And dotted within this positive sphere were the negatively charged electrons, like plums in a pudding or seeds scattered inside a watermelon.
Okay, I can visualize that. And the key idea.
The key was that the total negative charge of the electrons perfectly balanced the total positive charge of the sphere. So the atom as a whole would be electrically neutral. It was a neat idea, and it explained neutrality.
But I sense a but coming.
Yes, there was a but. While it explained neutrality, this model couldn't explain the results of experiments that came later. It was just too simple, ultimately. It didn't hold up to further testing.
Okay, so Thompson's pudding model was a start, but flawed. And this is where things get really interesting, right? With Ernest Rutherford, he did this famous experiment that just completely turned things upside down. Can you walk us through that, the alpha particle scattering?
Yes. Rutherford's experiment is truly iconic. He designed it to probe inside the atom, based on Thomson's model. This setup involved firing fast-moving alpha particles at a very, very thin sheet of gold foil, maybe only about 1,000 atoms thick.
And what are alpha particles exactly?
They're basically helium nuclei, so they have a double positive charge and are quite heavy, about 4 atomic mass units, much heavier than electrons or even protons.
Okay, heavy positive particles fired at a thin foil. What did he expect to happen based on the pudding model?
Based on Thomson's model, where the positive charge was spread out, he expected the heavy alpha particles to mostly pass straight through, maybe with some very slight deflections, but nothing major.
And what actually happened?
The results were, well, stunning, completely unexpected. First, most of the alpha particles did go straight through, undeflected. just as expected, suggesting mostly empty space.
Okay.
Second, though, a small number were deflected off course, some by quite large angles. That was surprising.
And the third observation, the really shocking one.
The most astonishing thing was that a tiny fraction, maybe 1 in every 12,000, didn't just deflect, they bounced back, almost straight back towards the source.
Bounce back from thin foil.
Exactly. Rutherford himself said it was almost as incredible as if you fire a 15-inch shell at a piece of tissue paper and it comes back and hits you. That's how shocking it was.
Wow. That quote really captures it. So what did these incredible results tell Rutherford?
They forced him to completely rethink the atom's structure. The fact that most particles went straight through confirmed his suspicion most of the atom must be empty space. The fact that some were deflected, and especially that a few bounced back, meant the positive charge couldn't be spread out like in Thompson's model. Instead, he concluded that all the positive charge and nearly all the atom's mass must be concentrated in an incredibly small, dense region at the center.
And that's what he called the nucleus.
That's exactly right. He called it the nucleus. He even calculated its size incredibly tiny, about 100,000 times smaller than the atom itself.
Amazing. So what did Rutherford's new model look like?
His nuclear model proposed this dense positive nucleus at the center, containing almost all the mass, and the much lighter negatively charged electrons. He suggested they orbited this nucleus, kind of like planets around the sun, in circular paths.
A nuclear atom, that sounds much closer to our modern picture, but was it perfect? You mentioned limitations earlier.
No, it wasn't perfect. It had one major critical flaw related to stability. According to the physics known at the time, classical physics, an electron orbiting a nucleus is constantly changing direction, meaning it's accelerating.
Okay. And why is that a problem?
Because accelerating charged particles are supposed to radiate energy continuously. So an orbiting electron should lose energy, spiral inwards, and very quickly collapse into the nucleus.
Uh-oh. So his model predicted atoms should basically self-destruct.
Pretty much. If Rutherford's model were completely correct according to classical physics, atoms would be incredibly unstable. Matter as we know it shouldn't exist. And that was a huge problem.
Right. That is a major issue. We exist, atoms are stable. So Rutherford's model, revolutionary as it was, needed fixing. How did Niels Bohr tackle this stability crisis?
Niels Bohr stepped in specifically to address this glaring contradiction. He proposed a new model in 1913 that kept Rutherford's nucleus idea, but added some radical new rules for electrons. Bohr put forward two key postulates, two fundamental ideas.
Okay, what were they?
First, he proposed that electrons couldn't just orbit anywhere around the nucleus. They could only exist in certain specific allowed orbits, which he called discrete orbits or energy levels. Think of them like designated lanes.
So not just any path, but specific ones.
Exactly. And his second postulate was the game changer for stability. He stated that while an electron is in one of these allowed discrete orbits, it does not radiate energy.
Ah, so it breaks the classical rule, but only in those special orbits.
Precisely. By saying electrons don't lose energy in these specific orbits, Bohr neatly solved the stability problem. Atoms wouldn't collapse. These allowed orbits, or shells, are often labeled with letters K, L, M, N, starting from the closest to the nucleus, or with numbers n equals 1, 2, 3, 4, and so on.
That's a clever fix. It keeps the nucleus, but makes the electrons behave in a new, quantized way. Did that complete the picture of the main particles?
Almost. Bohr's model explained stability and electron behavior much better. But there was still one more fundamental piece of the puzzle missing, related to mass. It wasn't until 1932 that J. Chadwick discovered the third key subatomic particle, the neutron, symbol N.
The neutron.
And its properties. The neutron has, crucially, no electrical charge. It's neutral. And its mass is very nearly identical to the mass of a proton.
And where does it live in the atom?
It resides in the nucleus, alongside the protons. This discovery explained the rest of the atom's mass. So the nucleus contains both protons and neutrons, collectively called nucleons. The only exception is the most common form of hydrogen, which just has one proton and no neutrons.
Okay, so the mass of an atom is basically the sum of its protons and neutrons in the nucleus. Electrons are too light to contribute much.
That's right. The nucleons account for almost all the atomic mass.
All right, so Bohr gives us electrons in stable energy levels, or shells. Now, how are these electrons actually arranged? Is it random, or are there rules for filling these shells?
There are definite rules. It's not random at all. The scheme for how electrons distribute themselves was worked out primarily by Bohr and Bury. The first main rule is about capacity. The maximum number of electrons a particular shell can hold is given by the formula 2n squared. Remember, n is the shell number, 1 for K, 2 for L, etc.
2n squared. So let's see. K shell N1 can hold 2 times 1 squared, just 2 electrons.
Correct. The L shell N2 can hold 2 times 2 squared, which is 8 electrons.
Helium shell N3 would be 2 times 3 squared, 18 electrons. N shell N4 gets 32.
Okay, that's the maximum capacity. The second rule is particularly important for chemistry. The outermost shell of an atom cannot hold more than 8 electrons, even if its 2n squared capacity is higher. This is often related to the octet rule.
The octet rule. Right, 8 is stable.
And the third rule is about filling order. Electrons fill the shells in a stepwise manner. Inner shells must be filled to their capacity before electrons start occupying the next shell outwards.
Makes sense. Fill from the inside out. So this specific arrangement of electrons, especially the outer ones, must be really important for how atoms behave chemically.
Absolutely crucial. This leads directly to the concept of valency. The electrons in the very outermost shell are called valence electrons. They are the ones involved in chemical bonding.
Okay, valence electrons.
Now, atoms tend to be most stable when their outermost shell is completely filled. For most elements, that means having 8 valence electrons, the octet. Helium is an exception, being stable with just 2 in its first shell. Atoms that already have a full outer shell, like the noble gases, are very unreactive. Their valency is effectively 0.
So valency is about achieving that stable outer shell.
Exactly. Valency is defined as the combining capacity of an element. It's a measure of an atom's tendency to react, to gain, lose, or share electrons in order to achieve a full, stable outermost shell, usually an octet.
Can you give some examples of how we determine valency?
Sure. Take hydrogen, lithium, or sodium. Each has just 1 valence electron. It's easiest for them to lose that 1 electron to get a stable configuration, so their valency is 1.
Okay, losing 1 gives valency 1. What about magnesium?
Magnesium has 2 valence electrons. It tends to lose both, so its valency is 2. Aluminum has 3 valence electrons, tends to lose them. Valency is 3.
Right. Now, what if an atom is close to having a full shell, like fluorine?
Good example. Fluorine has 7 valence electrons. It's much easier for it to gain 1 electron to complete its octet, get to 8, than it is to lose all 7. So its valency is determined by how many it needs to gain. In this case, 8 minus 7 equals 1. Fluorine's valency is 1.
Ah, so it can be about gaining, too. What about oxygen? It has 6 valence electrons.
You calculate it the same way. To get to 8, oxygen needs to gain 2 electrons. So 8 minus 6 equals 2. Oxygen's valency is 2.
Got it. So valency tells us how many bonds an atom tends to form based on its valence electrons.
Precisely. It's a fundamental property determining how elements combine.
Okay, we've covered the particles, their arrangement, and how that affects chemical behavior through valency. Now let's nail down identity. What makes an atom be a specific element, like carbon versus oxygen, and how do we define its mass precisely?
The fundamental identifier of an element is its atomic number, always represented by the symbol Z. The atomic number is simply the number of protons in the nucleus of an atom of that element. It's unique for each element.
So every single carbon atom in the universe has the same number of protons.
Exactly. Carbon has an atomic number Z6, meaning every carbon atom has 6 protons. Oxygen is Z8, always 8 protons. Hydrogen is Z1, always 1 proton. Change the number of protons and you change the element entirely.
Okay, Z defines the element. What about the mass? You mentioned protons and neutrons earlier.
Right. The mass number, symbol A, defines the total mass. Since the electron's mass is negligible, the atom's mass is practically all in the nucleus. The mass number A is defined as the total number of protons plus the total number of neutrons in the nucleus. These particles together are called nucleons.
Protons plus neutrons. So A equals Z plus number of neutrons.
Correct. For example, the common form of carbon, carbon-12, has 6 protons, Z6, and 6 neutrons. So its mass number A is 6 plus 6 equals 12. We often write this using a standard notation.
How is that notation written?
You write the mass number A as a superscript and the atomic number Z as a subscript, both placed just before the element's symbol. So carbon-12 would be mentally AC, nitrogen-14 would be OEA.
Got it. Mass number on top, atomic number below. Now, you mentioned common form of carbon. Does that mean there are uncommon forms?
Yes, and that brings us to isotopes. Isotopes are atoms of the same element, meaning they have the same atomic number, Z, same number of protons, but they have different mass numbers.
Same element, different mass. How is that possible?
It's because they have different numbers of neutrons in their nucleus. The number of protons is fixed for the element, but the neutron count can vary.
Can you give some examples?
Certainly. Hydrogen is a classic case. Most hydrogen is protium, which is just 1 proton, no neutrons. But there's also deuterium with 1 proton and 1 neutron, and tritium with 1 proton and 2 neutrons.
So all are hydrogen Z1, but with mass numbers 1, 2, and 3.
Exactly. Another common example is carbon. We have carbon-12, the Zc, 6 neutrons, which is most common, but also carbon-14, we're ACC, 8 neutrons, which is radioactive. Chlorine has isotopes too, chlorine-35 and chlorine-37, EuCl.
Do isotopes behave differently chemically?
Because they have the same number of protons and thus the same number of electrons arranged in the same way, their chemical properties are very, very similar. But their physical properties like mass and density and sometimes radioactivity can be quite different.
Okay. You often see atomic masses listed with decimals, like chlorine being 35.5. How does that relate to isotopes? Does any single atom have a fractional mass?
That's a great question. No single atom has a fractional mass number. That decimal value you see on the periodic table is the average atomic mass. Most elements in nature exist as a mixture of their different isotopes. The average atomic mass is a weighted average, taking into account the natural abundance of each isotope.
Ah, so for chlorine, the 35 and 37 isotopes aren't found in equal amounts.
Correct. Chlorine is naturally found as about 75% chlorine-35 and 25% chlorine-37, roughly a 3-to-1 ratio. So if you calculate the weighted average, 0.7535 plus 0.2537, you get 35.5. That's the average mass representing the natural mix.
That makes sense. Are isotopes just curiosities, or do they have practical uses?
Oh, they have incredibly important applications. For instance, an isotope of uranium, uranium-235, is used as fuel in nuclear reactors. An isotope of cobalt, cobalt-60, is used in radiation therapy for treating cancer. And an isotope of iodine, iodine-131, is used to treat thyroid disorders like goiter. So yes, very useful.
Fascinating uses. Okay, one last definition related to this. What are isobars? They sound similar to isotopes.
Similar name, but quite different. Isobars are atoms of different elements, so they have different atomic numbers, Z, different numbers of protons, but they happen to have the same mass number, A.
Different elements, same total mass number.
Exactly. It means they have a different mix of protons and neutrons, but the total number of nucleons, protons plus neutrons, adds up to the same value.
Can you give an example?
Sure. Calcium Cali has atomic number 20. Argon R has atomic number 18. They're different elements. But there's an isotope of calcium, calcium-40 IRC, and an isotope of argon, argon-40 RNRSAS. They both have a mass number of 40. They're isobars.
Calcium-40 and argon-40. Different elements, same mass number. Got it. Wow. What a journey we've taken today. From thinking atoms were tiny, hard, indivisible spheres, discovering electrons, protons, and nucleus, neutron shells, energy levels, valency, isotopes, it's really peeling back the layers of reality itself. For you listening, especially as you study, grasping these models isn't just about facts and figures. It's really about understanding the scientific process, how we ask questions, test ideas, find limitations, and build better explanations. It's a dynamic process.
Absolutely. And just to recap the ground we've covered in this deep dive, we looked at the discovery of the key subatomic particles, the electron, the proton, and the neutron. We discussed the early atomic models, Thompson's pudding and Rutherford's nuclear model, highlighting what they got right and where they fell short. Then came Niels Bohr's crucial model, introducing discrete energy levels to solve the stability problem. We covered the Bohr-Bury rules for how electrons are actually distributed in those shells. We explained the concept of valency, linking electron arrangement to chemical bonding power. We defined the all-important atomic number Z and mass number A. And finally, we clarified the difference between isotopes, same element, different mass, and isobars, different elements, same mass, touching on the vital uses of isotopes.
We really hope this detailed breakdown has given you a much clearer picture and a strong foundation for your studies, whether for boards or competitive exams. Keep that curiosity alive, keep asking questions, and keep learning. Stay tuned for more exam-ready insights, and make sure you subscribe so you never miss a topic breakdown.